Hello, my friends. This is Dr. Mohamed Nezami again, coming to you from Jerash, Jordan. How are you? Hope you're having a great time designing microwave and RF circuits and systems. Hello again. As for those of you that have watched me before, and all the new members, I welcome you. I have a YouTube channel in here. It's this here. I would appreciate if you go in and sign up, subscribe to the channel, and if you could please publish it, share it, and so on. So I have tens of videos on theory and techniques of microwave circuit designs, passive and active, and anywhere from DC to 35 gigahertz. Today, I'm going to continue the series that I have started, which was the design of KKA band SATCOM low noise block down converter, okay, which has about 5 parts. If you go to my channel, to the playlist, you will see the series in here, okay? Now, in particular, today, I am starting a new series. And the reason I started this is because I realized the feed mechanism for the LNB itself is really an area in which it requires more lectures. So I have created this sub list playlist, which I'm going to have several videos on the design of antenna to LNB structure design videos. Okay. Um, now, if you if you recall in this part here, okay, I started. This one was an overview of the LNB and their waveguide to microstrip line transitions. And you can just go to this part here. And it talks about basically, really, this is where we started. We started, say, looking at the waveguide to LNA transition to the first device and so on. And we went through these. And I have overviewed. Surveyed a whole bunch of LMBs and looked at how they do how is the vertical and horizontal uh, feed mechanism is performed. Okay, so we're going to start looking at this, and I have uh, several. I have created. Started from either a circular waveguide or a rectangular waveguide, okay, and then went on to creating I created my the Septum Polarizer, both for the square and for the circular waveguide. Just looked at the view, just overviewed these, and then I went on to looking at how you basically access the signal out via coaxial dual coaxials for the vertical and horizontal polarizations, and for both the circular waveguide and the rectangular waveguide. And the reason I'm going through both circular waveguide and the rectangular one is because if you look at any of these LMBs, okay, I'm going to try to expand this so we can easily, this is an LMB, a KU band LMB. And if you look at it, of course, the electronics is in this compartment here. But in the inside, you can see the probes, how they access. And this one here happens to be a circular waveguide. They all use circular horn, of course, but eventually they either feed a rectangle, a square waveguide, like it is in this case, where they have a little transition from circular to square waveguide, and that's basically because almost theoretically you could say with a small, tiny fraction of an increase in the current frequency. Both the square, of course, the electronics of this is on this side, as you can see. Now, both really equivalent. So the reason I'm sticking to looking at both the circular and the square is because we really they're equivalent. And some of the manufacturers of today's LNB feeds, they utilize square waveguide, and some of them utilize circular. And that's basically because some people, if they have aluminum casting for this, for high volume, or if they have a CNC machine, one for like gateways, expensive gateways, and space satellite, ground satellite stations. They either go either way. So, okay. Now, then I went on to basically both the feed for an LNB using both circular and vertical signals from the circular polarized signal. And this one here is similar to what's been used in these cheap, low-cost LNBs. Okay. So we're gonna go through these designs in every part. Okay. So and then finally to look at basically how do you interface a printed circuit board like it is in this case to a circular waveguide with a septum. Okay. And we're going to go through this for both the circular and the rectangular one as well. Okay. So we have either a dual feed, vertical and horizontal with septum, or we have similar to this, which we will look at. Let me see which one was it. This one here, where you have basically a sort of like a cheap septum, which is just a grid line that will basically act as a reflective quarter wavelength back short to one of the polarization, where it looks transparent to the other. So as you can see now, this series is busy. So I'm gonna split it into 4 or 5 parts. So today we're gonna look at some of the theoretical work of these LNB feeds. So let's get started. Just before, as a little advertisement for those that may have not watched me before, I operate out of Jerash, Jordan, inexpensively compared to operating from back the U.S. I have decades of experience working in the U.S. markets. And so I'm a semi-retired person doing some remote design work for clients in the U.S., India, Middle East, um, and Asia. So if you happen to have any design work that you don't have somebody in-house to handle, or if you like to offshore this, please send it my way. You can reach out to me via this email. I'm on LinkedIn also. Just type Dr. Mohamed Nezami. You will see me on there, or you can reach me out from my YouTube channel on YouTube. Okay, I operate very cheaply. Most times about $20 an hour. I give you ahead of time roughly how many hours it's going to cost you. I have designed stuff remotely anywhere from RF over fiber optic front ends, LNBs, LNAs, synthesizers, down converters, up converters, complete receiver, complete transmitter, power amplifier. All these I can do. I turn into you. I work with you from the concept. We build up specifications, and then we build up a system architecture. I have the design tools for system level modeling using System View and MATLAB, and then we move on to actual circuits design using either Keysight ADS or ANSYS HFSS. And then I would turn to you a Cadence or if you like Altium, if you like to work with that. I mostly work with the Cadence CAD tools to produce the actual PC board and the actual schematics. I have clients that will testify to you that they're happy clients with my work. So I would urge, if you have any need, please go ahead and reach out to me. Consultation is always free for first few hours. Okay. All right. So let's look at today's topic. So, like I said, we're going to look at today is basically the K-band antenna to LNB feed structure designs. Okay, and this is basically is the part that interfaces between the horn antenna and the low noise block down converter. Okay, now you can find many of these feeds, variety of way of doing these feeds. They can be anywhere from these ones in here to these ones in here, deep space probes like this one here, ship installed satcoms or airplane satcoms to on the move terminals like this, and even flat antenna panel as well. The feed in there is a very similar to this. So the concept of today applies to many of these platforms. Okay. All right, so just to basically review a little bit, I know you can please get back to my YouTube channel, and you can see the many of these basically videos on the LNB designs, and I'm not going to cover that today, but you can refer back to my channel. Many of these videos deal with LNBs and their system designs and system layout. Okay, but in today, I'm just going to focus on just give a brief, short introduction. So what we're trying to do is show you how to design the front end uh, interface part between the horn antenna and of course, you got the horn, you got the waveguide behind the horn, which is either square or circular, and then we have a mechanism that feeds to the LNBs. Now, the LNBs, of course, many times they don't operate with a single polarity of polarization. So they could be dual, and they could be frequency multiplexed, they could be polarization multiplexed, and so forth. So LNBs that we have covered in my series, if you refer back to the other videos, are, and I taken these with a from this source here, just a block diagram showing you how you go with the vertical and horizontal. Some of these LNBs, basically, they will switch the power on either one of these. You get a signal from the indoor modem to the LNB, basically, to tell it will go either vertical or horizontal. And then it goes in, and of course, we down convert, and there goes the IF. So you switch either between vertical and horizontal. Now, in some cases, we really simultaneously we're receiving these. Okay, so if in that case, then you have two feeds, dual feed, and then of course you have dual IF, and you could switch between them sometimes, like it is in this case. Okay, this case is where you can basically a quad LNB where you can access two IFs, two bands, okay, two KU bands, and then access two, which is four, because every one of these two has both vertical and horizontal. You can access that through a 2x4 switches like you see on here, RF switches. Okay, so what we're interested today in is how to interface between the horn and horn sub antenna, we call it, to a parabolic dish, and then go vertical and horizontal. Now, even though in here, basically, I'm saying that we're talking about parabolic feed assemblies, this really applies to also flat panel antennas like the Starlink and the other ones as well that are coming out nowadays. Okay. So other LNBs, of course, they involve same thing, except they utilize not discrete design. They utilize a chip, a mimic chip that does completely all the the phase lock loop and the down conversion, as opposed to these ones where it's done basically, it's built discretely. And I went through my videos, I went through this many times. So let's look at closer at what is a dual polarization antenna to LNB assembly. I took these from the IEEE, and basically you can see that what we have, of course, we have a parabola here that will collect the signals and focus it onto a horn. And then what we want to do is we want to get from the horn, this signal in here is either, most times, it is either left-hand side circular polarized or right-hand side circular polarized. So it contains both X and Y. You can say X and Y, you can say real and imaginary portions of the signal, where every one of those, they could either have the same information modulated, same information that you could utilize in comparing fading and fade out, or they could have totally independent modulations on them, like you would see in the direct TV or in the TV, KU band TV, KA band TV programming, where one channel would be, two channels would be on the same frequency, yet they are multiplexed. Basically, how you can decompose them is because of the orthogonality between them, where one, it was sent on the vertical and the other one on horizontal, or vice versa, okay? And this is basically, so this is the feed mechanism is the one that is responsible in collecting the signal with minimum loss, because it's very, now to preserve the sensitivity of the receiver, because such a low signal coming from thousands of miles away or from hundreds of miles away or kilometers, we need to have minimal loss between the phase aperture of the horn antenna and the ports of the signals. So to get the signal out, we have something called polarizer, be it Septum or some other ones. And you can look back on my in my lectures. I had a whole series on OTMs and polarizers, say. And then what it is basically is you take the circular polarized signal and decompose it both in vertical and horizontal with minimum loss, of course. And this is here is just an assembly, a concept assembly, where you can see that the signal goes through gradual change, where it gets to here, where it becomes gets into a square waveguide, okay, which is same as rectangular waveguide, except the A and B are equal, okay. And with a septum, which we will cover, and I did cover that before in the other pages, and gets split into both horizontal and vertical. And this is how you manufacture it, really, with a CNC machine. Is basically you have one piece here, one piece here, and then you have your metallic bars that implement the polarizer. Now the polarizers and OMTs, basically I covered many of these in the transition from circuit board to waveguides. These are covered here in my videos, and you can refer back to them, okay? They're here, like here's one, for example, the KA OTM design, okay? And then let's see, where's another one here? I'm trying to find it for you. I had several of these covered in my videos, so you can get back to them, okay? All right, so now looking closer at this, basically, this is the septum polarizer. It's basically what it is. It's you've got a transition, it transforms the signal, captures the signal into a square waveguide, and it then goes through a stair-stepped stepped septum, which basically I will show you in a minute, or you can refer back to my videos, which magically takes both vertical and horizontal circular polarized signal, either right-hand sided or left-hand sided. And what it does, it decomposes them into separate waveguides, rectangular waveguides, of course. You can see that the design, the assembly design is to go from square waveguide to two parallel rectangular waveguides. And of course, you can attach as a coaxial to waveguide transition on there as well, so that you can get back to cable. Okay. Now, of course, this is really done here. This is with CNCing aluminum pieces in here. This is really, and this, of course, this part here is off the shelf. You can buy this. This is really done for custom waveguide sizes and custom jobs like military radar installations, shipborne radars and SATCOM equipments. But for low cost stuff, we can't afford to do this. So we have to go to aluminum casting, and we have to go to cheaper methods than we would do here. Just here, I captured from the references, just from databases, various forms of this mechanism of dual polarization or circular polarization to LNB assembly transition interface. So you can see that these assemblies basically they start on one side on circular waveguide interfacing to a horn, a circular horn, like it is in here, and then of course they utilize either a circle waveguide or a rectangular waveguide like it is in here. And of course, with the septum, they can extract both vertical and horizontal. And you can go out either SMA or you can go waveguide, or you could go like what I'm going to show you today, which is basically to a BCB, straight to a BCB, because you want to launch that signal right out of the septum into the LNB electronics. And that's basically what we're going to cover. So let's just build, I don't want to cover the circular waveguide and the square waveguide from Maxwell's equations down to, I assume that my viewers are basically they have the background and they have the stuff. So basically, what I just want to remind you that for the lowest propagating mode into a circle waveguide, the equation that you extract the roots of the Bessel function to get the cutoff frequency is the TE11 mode, which is given by this equation in here, where the C is the speed of light, A is the diameter of the waveguide, circle waveguide. And then for a square waveguide, it's just like a rectangular waveguide. You just use the same equation, speed of light divided by twice the broad length, or the broad length in here is equal to the height also. So basically now, so you can see that if we want the circular waveguide to be exactly as a rectangular, as a square waveguide, and the reason we want to do this is because we can go and because we either want to go square or circular waveguide to interface to these circular horns. Now, depending on the design manufacturing capabilities that you have, either be it aluminum casting or CNCing aluminum blocks. So you can equate this equation to this equation here, and you're going to come up with a relationship that compares the square waveguide to the circular waveguide in terms of their cutoff frequencies, where you have either so what we see in here is that the cutoff frequency of the square waveguide as opposed to circular is really weighted by a factor which is 85%. Okay, so and of course it's divided by that magnitude, so which you can figure it out. So basically, if you want to make a square waveguide, is exactly interface it to, you could go back to back circular to square, and you would not feel a thing. Just a slight shift in the cutoff frequency, and of course, many times that's what people do. That's what this one in here is really doing. So that's what this one is doing. It just has a little flare and some you can find in the literature transition from a square waveguide to a circle waveguide with a little piece, and it's just to flare out the edges of a square into an opening of a circle waveguide. Now, mathematically, also the impedance of the waveguide, you can see that circular impedance is this, where for a square waveguide, it's this one here, which A has A's and B's, but A and B in here is equal, so they cancel out. So, which means if you compare this magnitude to this magnitude, that shows you that the impedance of a square waveguide is really going to have twice the impedance of a circle waveguide. The square waveguide has it twice because the B and A cancels in here because they're equal for a square waveguide. And you end up with 2 times this magnitude in here, which is twice this one. Of course, the wavelength doesn't change, it's the same for both. Okay, now, so let's look at the assembly of the whole business of going between from from a a from a cir from let me go to the circular waveguide one. The whole assembly of going from basically the signal that propagates down from the horn, this end would be connected to the horn, through the septum, and then through 2 halves of the circular waveguide, which becomes a rectangular waveguide, to go into this PC board in here, where we would pick the signal through probes, okay, be it printed probes like this one, or be it wire probes like it is in this one here, where we can go through a transition to the board on top, which I haven't done in this case. This business really is based on if you want to understand it and to design such an assembly, you would have to start looking at the waveguide E-field modes. How are they the pattern of these modes? If you remember, for circular waveguide, ladies and gentlemen, TE11, this is the pattern for them. Okay, so we've got horizontal or vertical, and this is how it works. Okay, and very similar to the square waveguide as well. We have horizontal and vertical, and of course, in that case, we refer to these as TO01 or 10, which in this case, really, if you could compare them to the rectangular waveguide, that's exactly what this is. So what we want to do in most times is we want to go from circular to rectangular, or from here to here, where we get both the 10 and 01 demultiplexed like it is in here, okay? And how we do that, gentlemen, with ladies, so how do we go? The mechanism is very simple, and I cover this in a separate video. You can go into my YouTube channel and look at the video of septum polarizer design. But basically, really what we want to do is we want to get a square waveguide or a circle waveguide and put a stepped septum that will demultiplex the vertical and horizontal portions of either a counterclockwise or clockwise rotating signal, meaning right-hand side or left-hand side circle polarization, if you want to call it that way, and to separate them into 2 rectangular waveguides. And then from here, couple into the LNB. And the design for this is really simple. It's just, we've got, I don't want to go through it again. I did go mention it, but we have these designs that people did back from 50 years ago, almost. And they gave us the dimensions. Basically, they involve the height and the length of all the stair steps. And they're normalized to the wavelength. So you can go to these papers and they show you how to you just get these coefficients and you scale them to your the waveguide dimensions and the wavelength, of course. So what we want to do is we will go from here into a T10 mode in here or O1, okay? And that's basically the septum, really. We can show it that it basically takes two signals, either horizontal or vertical, horizontal or vertical. And then, of course, while they propagate from this end to this end, they are subjected to this stair-stepped metal pieces. And what they do, you can look at the E field, how it varies, where if it is perpendicular, it really doesn't do anything. Where if it's parallel, what happens is it actually splits the E field into a 180 degree part, two sessions. And of course, we're going to the same aperture in both sides. And when you sum these, basically the E field in one case, like on the left-hand side in here, this waveguide in here, you can see that this one is equal to this one, but the opposite direction. So 100 degree out of phase. So these cancel, and these, they double, they add up. So which means that in this case, this waveguide will have a signal, and this waveguide will not have any signal. And in a moment, I will show you how that really works, okay? In fact, we can go to one of the septums that I have in here. Let's see, which one is this? This is, let's go to the one without the coaxial transition. Okay, this is the circular one. Let's go to the rectangle, the square one. Here's a square one. So right now, I'm exciting the wave port. You can see that it's coming. Oh, oh, that's not that one. Okay, so I need to be here. So you can see that the wave port, I'm exciting the wave port in here. Okay, this is the wave port, and you can see the E field modes. If you can zoom in, you can see that we've got mode one is like this, horizontal, vertical, and you got the other one, and I've got all the other modes up to fifth modes are shown in here. And what happened is if you can go to this one here, when we excite it with a signal, let's look at the E field, what it does. In this case, you can see that the signal is propagating in here, and it's basically coming in only to this port here. It's not going to that port, okay? And if you animate this, and that's the magic of the septum piece that is in there right now, which is the metal pieces in here. Let me just point out where the septums are these. Okay, so you can see the metal septum in there, okay? And and you can see that the signal is only coming on this port here and not on this port here, very little on this port. And of course, now if you want to if this signal were on rotating to the other side, let's go ahead and show you how what will happen. Let's say that the E field was, let me do this one is 90 degrees and this one is 0 degrees. So I'm just swapping the vertical and horizontal. And you can see it's going to go to this port. Okay, see that? What happened? Now, so depending on whether it's right-handed or left-handed, you're going to end up in one of these waveguides where the other ones. And this is really the principle of dual polarization LNB feed mechanism. Let me just show you how that is done by undoing what I did. Okay, you can see that the signal is coming to here. Okay, and the ratio of this to this, of course, that's the isolation or the axial ratio, and we can go through that and show you. So don't worry if you. I'm going to come back to this and detail it in more details in the next videos. So just theoretically, just show you what happens, okay? So we've got a square waveguide on one end, which is coming from the horn antenna or a circular waveguide, okay? And we've got a signal either, we've got either the vertical and horizontal components, depending on which one is 90 degrees from the other one. you get basically the waveguide, the signal coupling into two separate paths, okay? And you can see that here. So you can see that the signal goes in here, and of course, this one, this line is the metal septum in here. You can see it starts out small case, like it is here, all the way until it actually divides completely the square wave aperture of a square waveguide into two separate compartments representing two rectangular waveguides with half of the height. And that's really what's happening. You see that the E field is split here into two parts. Okay, where on the other side, where it's parallel, you can see that the E field, as soon as it hits that piece of metal in the staircase in here, it starts basically going into separate modes that are opposite in phase. And of course, they both share. This happens in both waveguides, and as a result, the E field will cancel on one or be minimum on one, while it's really maximum doubles on the other one. Okay. So now, just to view this from a circular polarization with the rotation, you can think of this as being two complex vectors. So one of them has a real part that's negated or 90-degree opposite to the other one. So meaning if you have let's say a signal in here that is rotating counterclockwise, you can see where the signal will end up. It's on this one here. Where if it's the other way around, the signal will get in the other one. And between this, the propagation into the septum from the smallest step to the largest step, which divides the square waveguide into completely two separate rectangular waveguides, you can see what really happens, okay, which is what I just showed. And you can go to many of these books, microwave books, and of course it details. So what I'm going to do in the next sessions is we're going to design both square and circular septum polarizer. And it's a very simple piece of metal work. Okay, so we will come to this, okay? All right, so let's get started on the LNB feeds. The first feed mechanism that I want to look at. Now remember, the septum polarizer is only a small piece that decomposes, demultiplexes, if you like to call it, the E field from a circular polarized signal into both vertical and horizontal, or from an elliptical polarization into whichever way directions you want. As long as you're really decomposing two orthogonal signals into separate paths so that you can take them, feed them to LNB, bring them down from K, KU, KA band frequencies down to the L band so that you can feed them to an indoor demodulator or modem or whatever. Okay? And of course, everything I said is true to the transmit side. Even though in here, I'm talking about the assembly feed from a receive point of view, really the opposite is also correct. So whenever you're doing, if you're doing to the other side, if you're transmitting, you really have two separate transmitters. You feed the ends of the polarizer, the septum polarizer, and then you can create actually, so two separate power amplifiers, two separate transmitters, two separate modulators, two separate up converter or bucks, if you want to say it, and it gets over to that. So the first thing I want to do today is let's start covering some of these. So this is a low-cost direct TV. I think this is used to be from Hughes. Okay, this is a dual horn. You can see that there's a dual horns in here with the circular waveguide in here that goes into this compartment in here and comes out with two IFs. And if you, you can get these from junkyards, flea markets, or laying around in your house, or you probably still have one that you're using it for TV, or you can get ones that are similar like these ones, okay, which I will cover today also. And you can see that this is what happened to the signal is it comes in from the circular waveguide in here. This is the end of where it is, ends up, and that's a septum in here. This piece in here is really you're looking at the last stage of this, which we extend usually so that we can have this separates both the vertical and horizontal, and then you have printed probes in here that couples the signal into an LNA, low noise amplifier. And so you can see this being done twice, done here, done in here, and you can go out. And this really, what this shows is that this LNB in here has four channels, which has vertical and horizontal from one, vertical and horizontal from the other one, and then so now this one here is really the mechanism, the feed mechanism to the LNB. And I like to consider this to be a separate subsystem, okay? And that's basically the concept of my talks in here. So we're going to look at this for various LNBs that I had my hands on in my box, junk box, or ones that I've worked on previously, and then show you the principle and the way to design these. So basically, this involves you really have to, you can't separate the electronics in here from the feed mechanism because basically you're trying to get the signal with a probe. And you can see that probe is connected right to the gasfets in here. This is a gasfet low noise amplifier. Even the DC is still even fed to the gate of this one here. In fact, the DC is on the thing in here because you wanna preserve the signal and not have any kind of losses in here. Okay, and the same way is done in here. Let's look at a closer look. So, like the ones that I'm going to show you. Basically, we have the septum in here, and we have the probes that picks up both the signals from the septum polarizer. But in here, really, the signal, when it comes in, it has to have a short back end so that a quarter wavelength extension of the circular waveguide above the probes. Okay, and that's what this led here. So what we do is we have a compartment, we have a lid that covers this. And this lid will have a quarter wavelength height piece in here. And this is really, let's go back to the simulations. And you can see here that, not in this, but in the ones that are hooked up to coaxial line. Let me go to that one. Okay, so you can see here, I will show you in the coming days that the let me just get the E field back on this one here. Oh, wow. Let me just reduce the, so we can see it better. Okay, let me, so 20. Okay. All right, so what we have is we have the probes pick up the signals in here. Let me go to the circular one so we can show that better. Okay, here's the circular one. Let's look at the circular one. So you can see that the probes in here, even though these are wire probes, but they apply also. This distance from here, the wave comes in, circular polarized signal from here, it propagates through a septum, and it gets separated in two parts. And these two parts, the placement of these probes, they have to have a back end, which is a quarter wavelength distance from the center of this probe so that the loading of the probe on here doesn't see any loading. And you can see that if it's short loaded quarter wavelength, that means it's open. So that this pen sees this open and the wave will see this open and bounce back. Okay, and gets in here with a zero phase shift with the signal that is incoming. And let me show you how that is done basically. Okay, so you can see that, let's animate this. Okay, hopefully, okay. So you can see that the signal, is really propagating and the signal couples into these ports, yet this one here, the distance between the back end and the probe really has to be related to a quarter wavelength of the of the propagating signal. Otherwise, it will load this, and that's a critical feature of this. And the way we do this, of course, in here, the waveguide, that's exactly how we implement it physically in an LNB. So we'll go through that in the coming sessions. Okay, so let's just have a closer look at this, and basically same thing. This is, oh, by the way, just I realized this while looking at this. You look at this side in here, for instance, this one in here, this goes to an LNA in here, but the other side in here is terminated, which is an interesting LNB in here, because that shows you it's a 3-channel one, because this one is really, even though the probe is there, but it's terminated. You can see there is a resistor, 50 ohm resistor to ground, and a capacitor, bypass capacitor on it. So they do this so that this is still balanced, and so I don't know why in this particular LNB has only a 3 channels, where this programming in here had only 1 in here. Okay, I doubt, you can see here the VA is connected to ground. So there is, if somebody thinks, no, the signal comes in and goes through a VA to the other side of the board. No, it doesn't. Okay, this is grounded. Okay. All right, so let's look at this again. We have a septum, and the piece in here, this piece that sticks out, is basically an extension of the septum that will come in and hit this so that you can go to the quarter wavelength cap, the back short. So that's what it is, this one here. That's why it's sticking out. In some cases, the partitioning of the circular waveguide short back end is done in the housing itself. It's not, when you see it, I'll show you in a minute what I mean. So this one doesn't have to stick out. The cap comes in with a built-in divider. Okay, now this is again in here an interesting one that I looked at. You can see the septum. You can see the stairs in here. There they are. You can see 1, 2, 3, 4. That's a 4 pieces, unlike what I've drawn in here. This is only used for illustration. Okay, so both, of course, they have both the vertical and horizontal going separate LNAs and then on to the LNB. Here's another one, which is interesting. And this one here, let me, okay, here's what I was talking about. This one here, you see the cap, it comes in with this partition in here, and this, of course, in the board itself, they put the transition as well, with VS assuring the ground, the top and bottom of the board, which meaning connecting the back end of the circular waveguide to the feed horn circular waveguide to make sure it's electrically connected well. Okay, and of course the probes are right here, and they made this cross just so that they can give it rigidity, mechanical rigidity and stability. Okay, same thing, you know, when you review these LNBs, you can see that the designers were very creative in many cases. These were designed in the 90s and 2000, early 2000s, so a lot of good designers back then. So here's another one. Well, this is the same one, except we're having a closer look at this, okay? And so how do you model this? How do you design this? Of course, we can go back to my, I will show you that in the next sessions. And that's basically, here it is. Here's one. Let me go to the circular one. This is one, okay? So this is my design here. So you can see that here's the septum. It comes in, it divides the circular tube or waveguide, and then here's the board. Here's the BC board with an opening for the printed circuit board. And I have 2 probes right now. This is Rogers 4003, the material, and I have 18 mil width line in here, which feeds the signal. And here are the V's, okay? And here is this cap in here. You can see that this cap in here, this cap here, is basically the quarter wavelength extended beyond the board that offers basically the back end short to the probes. both the vertical and horizontal. And this piece in here that I colored in blue, this one here, that's the divider between the horizontal and vertical. And just to show you how that this is really working, let's go to the E field, and you can see that right away, you can see how it is bright on one side and dark on the other side. That's because right now I have it set up so that I can receive the signal on this port, and I don't know which is which. So, and in fact, let's animate this so you can see how cute this is. And this is, it takes a lot of work and to try to preserve the loss of this. Remember that this is in front of the LNB. So really, this either kills you or revives you on the concept of the noise figure. Okay, because you want to try to do this by maintaining that the loss is really low enough so that you can pass the budget link on the G over T that you're specifying. So you can see the signal, how it's propagating in here, the circular polarized signal on this side, and then it goes out and cancels on one side, it cancels, while on the other side, it completely goes into the board. And this would be where your LNB starts out, okay? So what I have in here, I have cut out in the cap in here so that I can route the signal. And of course, you can always go back and reverse. You can reverse the polarity of the, you can assume that the signal is counterclockwise or clockwise like the other side. So you can just basically reverse the 90-degree phase shift on the between the polarizations, and you can see right away that I'm going to go to the other side. Okay, there you go. So it's already computed and shifted the signal to the other side. Okay, you can see how it is doing it. And of course, you do this while, of course, really, it's very critical that the return loss on both the microstrip and the other side, it's a lot of work, a lot of optimization. And of course, you maintaining that you can see the impedance. One is 49 ohms for the microstrip, while it's 750 for the waveguide on the circular polarization section. Okay. All right. So let's get back to this. So we're going to, ladies and gentlemen, don't worry about that. We'll get into more of this in the coming sessions. Just to show you more interesting LMBs, here's one that has, let's see, that has a 1, 2, 3 waveguide signals coming in. 3, that's 6 programmings on this one here, 2, 4, 6. And you can see the waveguides in here, how it's the interface, the rectangular waveguide. This one here is really a square waveguide, unlike this one here. It's a circular waveguide. So that's why I kind of kept both square and circular waveguide to illustrate, because and here's another one in here. You can see the vertical and horizontal probe, and you can see the probe is going right into the LNA, which is going to the bandpass hairpin bandpass filter and onto the rest of the down converter that way. An interesting thing to mention here, this one is 45 degrees slanted, and if you know why that is, please write me in the comments. But I was looking at that and wondering, why did they do it that way? There's no reason not to do it this way, but you would have to. I have no idea why they went into 45-degree offset. Here's another one where it doesn't have the 45-degree offset. Basically, you have a lower frequency in here than here. So we have one square wave guide here, another square wave guide, another square wave guide, and you have 6 programmings on this. So you pick up the signal and you go through with them. So this is an interesting also one. All right, so we start out in my designs. I've used Rogers material, 4003, 8 mil height. So a 90 degrees, about 162 mils length on this substrate, and the 50 ohm line is about 18 mil. Okay, 17 and fractions. Okay. So that's basically what we're going to do. I'm going to go ahead and just show you how you can actually design this using both rectangular, I mean a square waveguide and a circuit waveguide. So I'm gonna wait here and start a new video for you on this. Okay, so I'm gonna cut this so that we don't have a very long videos. And basically next we're gonna go into other forms of this, which is an interesting concept also. So we'll see you in the next part, ladies and gentlemen. Thank you. This is Dr. Mohamed Nezami again. And again, we're covering the KU, K-band antenna to LNB feed structure designs. Okay. Thank you very much and have a great day.